So now we'll discuss one point like now. So we had the multivariate distribution or multivariate discussion, right? Now, so in that what we have done is we had the discussion related to single random variable where we extended it, and we had a discussion related to joint distribution. Now the question comes, so is it possible for us to extend this multivariate discussion in terms of conditional probabilities? If so, what happens? Now, if you recall the conditional probability discussion what we had, so suppose if I write like this, P of A given B, if you remember, right? So P of A given B, that is, this is a conditional event where this is a conditional probability. So where this B is the first event, the already happened event followed by next event. So where this is P of A intersection B by P of B. Right? So this already we are familiar in terms of conditional probability where A and B are two events. Similarly, the other way, that is, if you want, I'll write that also. That is P of B given A, where A is the first event happened and followed by the second event. So this is P of A intersection B by P of A. Right? Okay. Now the question here is whether we can extend this discussion in terms of random variables. Here this discussion is with respect to two events where B happened first followed by A, or A happened first followed by B. So is it possible for us to use this discussion where A and B are replaced by two random variables? So that is the point of discussion. So that is whether we can have P of X given Y, right? It is something like where Y equal to 2, that is where already the first event happened where we selected the events where two heads are there, right? So from that we are going to have, suppose X equal to 1. So from this we are going to select where X is a random variable related to tails, suppose. So first we are going to select two heads, from that we are going to select one tails, that is, right? So here, is it possible for us to have the discussion or not, right? So now yes, so now this is nothing but we can write this as P of xy by P of y x y. So this is nothing but in the same lines. So the conditional event where x and y are random variables, in this case discrete random variables, then it is P of xy like P of A intersection B, and here the sample space is y. That means we'll have the probability distribution with respect to y only. Therefore, so P of y comes here. P of y is our sample space. So yes, we can extend the discussion what we had in terms of conditional events to two random variables x and y. So if you remember, so here this is P of xy is nothing but giant probability distribution function, right? And this is the marginal probability distribution in terms of y. Okay. Similarly, I think it is understood. If I take P of y given x, then it is P of xy, which is the joint probability distribution function of both the random variables, and the denominator is in terms of x only, that is marginal with respect to x. Okay. So like this we can have the joint conditional probabilities, right? So now this is the discussion whatever we had is in terms of discrete random variables. Suppose if x and y are continuous random variables, is it possible for us to extend the discussion or not? Yes, it is possible for us to extend the discussion. So then what happens? Now it is also very simple. So that is f of x given y, then it is f of xy by fy of xy. The same discussion carries here. Right? Suppose here f of xy is nothing but giant probability density function. Giant probability density function. And this f is a separated one, that is a marginal with respect to y. Therefore, this is marginal probability density function with respect to y. In the same lines, say the other probabilities also we can define, where f of y given x, then it is f of xy by f of x in terms of x and y. That is, here this is giant probability density function in terms of x and y, and this is marginal with respect to x. Marginal with respect to x. So like this we can have the giant conditional probabilities in both the cases. If the two random variables are discrete, then we'll have conditional probabilities like this. If the two random variables defined are continuous, then the conditional probabilities are defined like this. Right. So like this we understand the concept what we discussed in terms of two events, and we extend this in terms of random variables. In both the cases, one is discrete, other case is continuous. And one more point to add in the discussion is, suppose if I take the giant distribution p of xy or f of xy, then I had marginals corresponding to this. That is, I had marginal with respect to x, I had marginal with respect to y. Right? So this is a giant in terms of x and y, and from this I am able to have the marginal with respect to x and marginal probability distribution function with respect to y. If p of xy equal to, that is joint distribution equal to the probability distribution function of both the random variables equal to the marginal of x into marginal of y, then the two random variables are called as independent random variables. This is one point to add. If then immediately I think I hope that you recollect the independent events condition, that is p of a intersection b equal to p of a into p of b. Right? P of a intersection b equal to p of a into p of b, then we use it to call a and b are independent events. In the same lines, p of a intersection b here nothing but it is a joint, and p of a is nothing but the marginal with respect to x, p of b is nothing but marginal with respect to y. So therefore, this is one condition where we define the independent random variables if they are discrete. Now the same in terms of continuous random variables, that is f of xy, that is the joint probability density function of x and y, equal to marginal of x into marginal of y, then the two continuous random variables are said to be independent random variables. Thank you.